The last thing that we'll look at in section 3 is the rigorous mathematical definition for relative extrema. Number 1 will be the relative maximum, number 2 will be the relative minimum. And I'll underline those, relative maximum and relative minimum. So looking at the picture that I have drawn, we'll use this as a sort of a playground for us to explore how this definition works. It says a function value f of a is a relative maximum of f if there exists an open interval containing a. So what I would like to notice is that if I was to take this point and if I believe that it is the relative maximum, then I would like to apply this definition to it to prove that it is. So taking this point straight down to the horizontal axis, I would label that as little a, which means if I carry it horizontally to the vertical axis, that would be the value f of a. So we believe that this would be a relative maximum. Based on the previous example, we are changing from increasing to decreasing at that point, and so that would be something that we would consider a sort of a top of a hill type situation. That's an informal understanding, but it's also the intuitive understanding that most students already possess. So how does this formal definition, this rigorous definition, work with our intuitive understanding? It says that there has to be an open interval containing a. Open interval containing a, and a has to be an element from the domain of your function. Now, certainly the point that we have chosen is a part of the function. It's one of the ordered pairs, so little a must be an element of the domain. So if you pick a point that's on your curve, you're automatically going to be working with something that's in the domain. So that's already taken care of. But the open interval part, we need to make sure that we draw in. The open interval part, let me use green, is going to be here and here. So we're just going to create some kind of open interval that has a contained in it. Now, most often, it's easiest if you think of a as being in the middle of that open interval. Now, here's the condition. It says the phrase, such that f of a has to be larger than f of x for every x value that is not a in the open interval. Well, if I look at the open interval, there are a lot of other values that I could pick that are not a. For example, let me pick this point. I'll call that my x. So if I take that x and I carry it up to the curve, and then I mark that point, carry it over to the vertical axis, that would be the location of f of x. Is the f of a larger than f of x? Is f of a greater than f of x? And here the answer would be yes. Now, will that be true for any x that I pick in the interval that's not a? So pick a different place. Let's use a different color. Let's say purple. I pick another point. Let's pick, say, this one right here. And we'll call this the purple x. And if I use that, I carry that up to my curve. Now, this point is a little bit closer to the point that I'm calling the relative maximum, but if f of a truly is the relative maximum, then it should be higher than the point that I've marked there in purple. And the details become a little fuzzy here trying to fit it all in, but you can see where this mark is located with the purple. It would be below f of a. And so you can imagine any point that we would pick around a is going to have this condition. That is the definition of a point representing a relative maximum. Part 2 of this definition is very similar, and it talks about being able to identify something as being a relative minimum. So in this case, I would like to believe that this point is going to represent a relative minimum. So I would mark that as being B on the x-axis, and then if I carry that point over to the vertical axis, that would be the location of f of B. So we can apply this open interval concept around B just like we did around A. And if I select a point, or select an x value that is inside of my open interval, then I can carry that up to the curve, and then I can carry that over to the vertical axis, and then that would represent my f of x. And when I look at my condition for relative minimum, it says that f of b has to be greater than f of x, or excuse me, f of b needs to be less than f of x. And that's exactly what we can see. The connection between these two things is that the f of b has lesser value than the f of x does there. So that would be true for every point that is in the open interval around B. And this is known as the formal definition for relative maximum and relative minimum.